Here we're going to look at another number patterns and sequences problem. So here we have two parts. So for the first part, we need to consider an infinite ladder with an infinite number of rungs. It is given that a rung is 7 centimeters longer than the previous rung and that the length of the first rung is 20 centimeters. And part A is asking us to find the length of the nth rung and hence find the length of the 100th rung. So I just do some observation. So notice that on the first rung, we have our rung being a length of 20 centimeters. So everything for n equals 2 and n equals 3, we're just essentially adding 7 centimeters. And notice that this sequence looks like an arithmetic sequence, and indeed it is. So notice that we can conclude that, let's just say an will be the length of the nth rung. This could be equal to 20 plus 7 times n minus 1, or if we would just expand it, it will be 7n plus 13. Now, for those who don't really know what arithmetic sequences are, notice that n minus 1 is essentially means the number of times we're adding 7 into our expression right here. So that's how we get this number. The length of the 100th rung, well, we can just substitute n equals 100 into here, which will leave us with 700 plus 13, or 713 centimeters. For part 2 of part A, this is a bit interesting. So as the rungs goes towards infinity, what does the length of the rungs approach to? So let's just observe this sequence. Notice that this sequence works by just adding 7s on and on and on until we approach infinity. We're just like adding a bunch of positive numbers to each other, and then we eventually approach at a number that is bigger than any finite number possible. So hence, we can conclude that the sequence approaches infinity. Now let me just solve this using limits for those who know what limits are. So essentially, we can just take the limit as n goes to infinity of a of n, which will be just 7n plus 13. We can kind of plug in n equals infinity to here. Notice that 7 times infinity is infinity, and anything plus infinity is just infinity itself. So this will approach infinity. For part B, we can consider a second infinite ladder with, again, an infinite number of rungs. And instead, we're given that a rung in this ladder is half the length of the previous. And it's also given that the length of the first rung is 32 centimeters. First, we need to find the general form of the length of one rung. Let's just say that b of n will be the length of the nth rung. Now let's just observe values for n. So for n equals 1, that will be just 32 centimeters since it is just the first rung. For n equals 2, it will be 32 centimeters times a half, since a rung is half its length of the previous. And n equals 3 is this just, again, very similar, and then so on. Notice that this looks like a geometric sequence, and indeed it is. So we can conclude that b of n will be equal to 32 times a half to the n minus 1, where essentially n minus 1 is basically the number of times we're multiplying by a half. Or let's just make this a little bit nice. We can make it as 64 times a half to the n, if this n minus 1 bothers you. Now to find the length of the 10th rung, we can just substitute n equals 10 to this equation. So 64 times a half to the 10th, which will be just 1 over 16 centimeters. And then we need to answer, what does the length of the rungs approach to as the rungs goes towards infinity? Well, this is just pretty similar. Well, one can solve it by using limits, so we can have the limit as n goes to infinity of b of n, or 64 times a half to the n. Well, notice if you plug in n equals infinity to here, well, a half to the infinity, we're essentially just multiplying a half an infinite number of times, which will just approach 0, and 0 times 64 would just be 0. So this will approach 0. Solve this in a non-calculus way, well, notice right here. Notice that's 32, there will be just 16 centimeters, this will be 8 centimeters. And notice that essentially, the length of the rungs decrease. One thing to notice that the length of these rounds will never be negative, or in other words, they'll be positive. So we can say that B of n is always positive for all natural numbers n, because obviously in Euclidean geometry we cannot have negative lengths. And notice that we're also multiplying by a positive number, so there's no negative shenanigans right here. And if the sequence reduces right here, it will just keep on reducing and reducing, and eventually it will approach a number which is very, very close to 0. So again, it will approach 0 in this case, which ends this video.